Hello everyone, welcome back to another episode of Math Unlocked. I'm your host, Mrs. Rhodes-Grierson. Today we're going to be solving a pair of simultaneous equation, not using elimination, not using substitution, but using matrices. That means you'd have been familiar with the concept of matrices multiplication and matrices inverse. Now what are we required to do? We're going to take it step by step. In solving a pair of simultaneous equations using matrices means I need to create three matrices. I'm going to create matrix A, matrix X, and matrix B. Since it's an equation, my first matrix will be my coefficient matrix, my second matrix will be my variable matrix, and my solution matrix B is actually the solutions of the two simultaneous equations here. Now notice that if I say the A times B is equal to A times X is equal to B, literally what it's saying up here is that each coefficient multiplies either X or Y and it has a solution. So in my A, I'll have my coefficients 3, 2, 5, 4. In the matrix X, I'll have my variables, and notice here I'm writing them in terms of a column. Why? The application of matrices multiplication says that the rows multiply the columns. So that means that if I should multiply A times X, it should give me back my simultaneous equation that I have here, which means that X and Y must be written as a column in order for that to be true. What is that equal to? First, a solution is -1, and my second solution is 6. Now, in order to use matrices to solve, it therefore means that matrix X needs to be the subject of the statement. In order for that to happen, I need to eliminate A from here. How do I cancel it? To cancel a matrix, I must do the inverse of the matrix, which means that A inverse would cancel matrix A. And if I have an equation, whatever is applied to one side of the equation here must be applied to the other side as well. Notice I placed A inverse in front of B. It means that the matrix will be to your left and B will be to your right. So your solution stays on the right. Now that therefore means that I need to know what then is A inverse. We would have covered finding the inverse of a matrix before, but let's do it again. The inverse of A, I need the determinant of A, and I will need the adjoint of A, because in the formula to find the inverse, it's 1 over the determinant multiplied by the adjoint. So we first start out by finding what is the determinant of A. Symbol, these two lines with a letter in the middle, indicates that it's the determinant of A. Once we're doing inverse, we are required to identify the diagonals of the matrix. So that's diagonal 1 and that's diagonal 2. What will I do with them? The determinant says to multiply the products of the elements. So these are the elements on the leading diagonal. I'll do the product of the leading diagonal minus the product of the non-leading diagonal. That gives me 12 minus 10. Therefore, the determinant is 2. The adjoint is a matrix itself of the original by rearranging the elements on my diagonals. Diagonal 1, which is my leading, I'll switch the positions of those. Diagonal 2, which is my non-leading, I'll change just the sign. Signs only, not the position of the non-leading, signs only. Of the leading, positions only. Of the non-leading, signs only. So this, therefore, is my adjoint. Now that we have the determinant and the adjoint, I can now do the inverse. Alright, so here we are completing the inverse process. So A inverse is equal to 1 over the determinant of A times the adjoint of A. Since we have a fraction multiplying our matrix, we're going to have all these elements here written as fractions as well. So all our whole numbers, I'm just going to be placing those over 1. And I'm going to be doing my multiplication. So when you have a scalar quantity, one single number multiplying your matrix, it's used to multiply every element inside. So the first one is 4/2. The second one is -2/2. The next one is -5/2. And the next one is 3/2. I'm going to simplify the fractions that can be simplified. First one, 4/2 is the same as 2. -2/2 is the same as -1. -5/2 remains as -5/2, and 3/2 remain as 3/2. So this, therefore, is the inverse of matrix A. What am I doing with that? Remember now that we said that we wanted to find x and y, which means that we would have needed to take A to the next side, which is A inverse. So A inverse now needs to multiply B. So let us complete that process. We would have found the inverse. We want to take that inverse, and we needed to use to multiply the elements in B. So that's 2 -1, -5/2, and 3/2 is now multiplying -1, 6. When I have done that, what it would have solved for is the values of x and y. So let's go. Remember that when we're multiplying a matrix, from the first matrix on your left, you'll identify your rows. So I'm highlighting row 1, row 2. From the matrix on my right, I'm identifying my columns. In this case, it's one column. So my solution matrix, or my resultant matrix, should have 2 rows and 1 column. And that is solving for x and y. Come with me. Row 1, column 1. 2 multiplies -1 plus -1 multiplies 6. Simplifying, this is -2 plus -6. That gives me -8. Next step, these are fractions. I'm going to make these fractions as well. -5 multiplies -1 to give me a +5/2. 3 multiplies 6 to give me, did I write that? Let me write that. -5/2 times -1/1 plus 3/2 times 6/1. Simplifying this, we will get a +5, since a negative times a negative gives us a positive, plus 3 times 6, that's 18/2. 18 plus 5, that will be 23 halves. We can convert this to a mixed number, or we can leave it as a fraction. But in this case, I'm just going to be leaving that as a fraction there. So double checking, negative times negative, that gives me +5. 2 times 1, that's 2. 3 times 6 is 18. 1 times 1 is 2. Adding my numbers, I get 23 halves. What does that result in? It means x is -8 and y would be 23 halves. And that solves my pair of simultaneous equations for the values of x and the values of y. I could write a concluding statement that x is equal to -8 and y is equal to 23 halves.